Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering, Greater Kolkata College of Engineering and Management, JIS Group. Today I am going to take the class of Signal and System, and in this Signal and System subject, today's topic will be classification of signals. In previous lecture I have described different kind of signals. Today I am going to describe three different kind of signals. Those are very important for our syllabus. Okay, so let's start. This is the lecture 2. Okay, today's discussion points are even and odd signals, continuous and time complex exponential signals, discrete time complex exponential signals, and sinusoidal signals. In previous lecture I have described the even and odd signals. In today's lecture I am going to give the explanation of different kind of characteristics of even and odd signals and its significance. Okay, so let's go to the next slide. Okay, the characteristics of odd even signals. What are they? In case of an important fact is that any signal can be broken into a sum of two signals, one of which is even and one of which is odd. Consider the signal, it's an even signal sign, x function of t is equal to 0.5 x function of t plus x function of minus t. Here x function of t is an even signal and x function of minus t is an odd signal, which is referred to as the even part and odd part similarly. And in case of odd part, we also taking in account the odd function x function of t is equal to 0.5 into x function of t minus x function of minus t. It's a simple exercise to check that even part is in fact even, that the odd part is odd, and that x function of t is the sum of the two. Exactly analogous definition hold in the discrete time case. So I'm going to explain the time function, and in case of this slide, in the next slide I'm going to describe the discrete time signal, which very much will be true for continuous time signal. Okay, so let's describe how it works in the next slide. Okay, now if you take a very close look in this slide, that we have a signal. This is a function of x function of n. It's a discrete time signal where x function of t is equal to 1 when n greater than equal to 0. When the integer value is, if the integer value is greater than 0, then the signal value will be 1 in each case. And if value of n, the integer value of n is less than 0, then the signal will be reside at 0 point, and the value of the signal will be 0. So this is the basic signal that we are going to decompose. Now if you decompose this signal, what we have here, we got two signal, which basically this is if you take a very close look, this is an even signal. How it works? Look, this is in case of this signal, if this function describes this signal, how? Look, n less than equal to 0. When n is less than equal to 0, the value of the signal in every discrete, if in each integer value, the value of the signal will be 1.5, means 0.5. At n is equal to 0, at n is equal to 0 integer value, the value of the signal will be 1. And it's similar for n greater than 0, the value will be half. This is an even signal. This is a very even signal. If you as we have described in the previous slide, that in case of even signal, the immediate image of this signal will be same as the basic signal. So this is an even signal. It is itself as an even signal. So this is the value of the even signal. Now if you take a closer look at the third picture, where I have described the odd signal, how it works. These are odd signal from, just by seeing it we can understand these are odd signal, because if you take a mirror image of this very signal, we will get a different signal. It will not be the same as this. If you take a mirror image of this signal, it will give a very similar signal. But in case of this signal, if you take a mirror image of this signal, we will not get that signal back. Now if we describe this odd signal here, what we have here? We have the function describe the signal. How? Look, x function of n is equal to plus half, where plus half in case of n greater than 0. Signal is saying n greater than 0. When n greater than 0, the signal value will be half. In case of n is equal to 0, the signal value is 0, and n less than 0, the signal value will be minus half. Now, as we have can describe this, that if we add this signal and this signal, we'll get this signal. How it will happen? If you take a very closer look here, look, in this signal, at n is equal to minus 1, the value in even signal, n is equal to minus 1, the value of the signal is half. And in the same point, the value in case of odd signal, at n is equal to minus 1, the value of the discrete signal is minus half. Now, if we add both of them, what we'll get? We get this. This part and this part will be cancelled out, and we will get this. In a similar operation, we can take care all of this operation by this. The similar operation we can take place, and we'll get this. In both cases, the same similar things will happen. This is plus half, this is minus half, and if we add them, we get 0. This is plus half, this is minus half, and we add them, we get 0. The similar is here. This is half. N is equal to at n is equal to 1. This signal's value is half, and this case the signal value is half. Now, if we add them, we get 1. So, the whole all the definition that I've given right now, all the explanation that I've given, is the significance of this is that any signal, the basic fundamental property of an even odd signal is basically any signal, any arbitrary signal can be decomposed into an odd signal and an even signal. This kind of thing will be beneficial when we are going to study modulation and demodulation in case of communication. When you have to characterize a signal, we have to verify and characterize describe a signal. We'll use this kind of property of this signal. One signal can be decomposed into two different signals. One will be even, another will be odd. So, okay, let's go to the next slide. Now, in this slide, what I have described is continuous time complex exponential signal. Now, complex exponential signal is nothing but an exponential signal, where the signal will be described by this function. X function of t is equal to c e to the power alpha t, or at. This a could be anything. Now, as the value of t increases, the signal strength of the signal will be increasing, will be behaving this way. If you take this picture, a close look at the picture, if you increase the value of t, it will increase this way. An exponential curve will take place. Curve will be created basically. Now, this is the increase exponential signal, and in this case, as the t increases, the exponential, in case of this, the function will be c e to the power minus alpha t, or at. Now, as t increases, the signal will decrease from this point. As you can see from this picture, that as t increases, the whole value of the signal is decreasing. It's just decreasing. It's just this way. It's just decreasing. Okay, so this is the basic fundamentals of a continuous time complex exponential signal. Now, let's go to the next slide. Now, as you have described that continuous time exponential signal, now I am going to describe the periodic complex exponential signal and how it will convert into a sinusoidal signal, or a complex exponential signal is basically a sinusoidal signal. Let's start. Now, as I've said in this slide, that a second important class of complex exponential is obtained by constraining A to be purely imaginary, specifically considered. Simple, that what you have done in the previous slide, what you have seen, that c e to the power alpha t. Now, in place of alpha or a, I have considering a j omega 0. We have taken a purely imaginary number that we have already know from our previous studies in 11. Now, if we take a very close look at x function of t is equal to e to the power j omega 0 t. Now, next, what you have done, an important property of this signal is that it is periodic. How you can understand it from a mathematical process, through a mathematical process. We want to understand that. To verify this, we recall from equation the very previous equation that we have already in the previous slide. I have already given that equation. That is what I have referred here, 1.11. That x function of t will be periodic with period t. Now, we can write that we have assumed that this e to the power j omega 0 t is periodic with time capital T. Now, we can write this. Now we can write this in this very manner, right? E to the power j omega 0 into t into e to the power j omega 0 capital T. Now the most important part is here is that it follows that for periodicity we must have e to the power j omega 0 capital T is equal to 1. Now why? Because in case of what we have learned from the previous lecture, that a periodicity means after a specific time interval the same signal will be repeated. Now the basic signal is this. So what we have here is this, but to follow the periodicity principle, we have to get back to the real signal. The real signal is this. So to get back here, we have to have this value 1. Now what you know from the Euler's theorem, that what you know from the Euler's theorem is 1 is equal to e to the power j 2 pi. We have already known it from the 11-12 study that in complex number that the value of 1 is equal to e to the power j 2 pi. Now if we consider this 1 is equal to e to the power j 2 pi. Now if you compare both, what we will get that j omega 0 t is equal to 2 pi. From that we conclude this. Both the j will be crossed, and from this t is equal to will be 2 pi by omega 0. It's a mod value, so because we only take the amplitude value, we only take the absolute value of omega. Now what do we get there from? We get this. Now if omega 0, now this omega 0 is equal to 0, then x function of t is equal to 1, simple, which is periodic for any value of t. It means that exponential function, when you take a alpha value is equal to j omega 0, at omega 0 z, that signal will be periodic. Now if omega 0 is not equal to 0, then the fundamental period t0 of x function of t, that is the smallest positive value of t, for which equation 1.3 holds, is this. As simple as that. If we have omega 0 is equal to 0, then we don't have to consider anything. We know that the function or the signal is periodic. Now if omega 0 is not equal to 0, then we have to compare it from the Euler's formula, where we know that 1 is equal to e to the power j 2 pi. So we compare that e j omega 0 t is equal to e j 2 pi. We compare the exponential values and we get this. And this is the periodicity of a complex exponential signal. Now what you have gained from this is that the signal e to the power j omega 0 t and e to the power minus j omega 0 t have the same fundamental period. That's a very important factor. A signal closely related to the periodic complex exponential is the sinusoidal signal. Basic thing is that if we take a periodic complex exponential signal, it's basically a sinusoidal signal. It will be described in the next slide. You take a look. This is the time period that we have obtained from the previous slide, and this is x function of t is equal to a cos omega 0 t plus 5. Okay, next slide. Okay, what we have done there, nothing but that if e to the power j omega 0 t, this could be described as this. It's a cos plus omega 0, a cos omega 0 t plus j sin omega 0 t. We can write this. We know this from complex number system, that we can express it to the power exponential j omega 0 t is equal to this. And in the previous slide, what you have described is that this function e to the power j omega 0 t is a periodic complex exponential signal. So eventually this periodic complex exponential signal eventually described as a sine or sinusoidal signal, basically a sinusoidal signal, because this function can be expressed as a cos omega 0 t plus j sin omega 0 t. Okay, let's go to the next slide. Okay, we are here. Now this is the simple description of nothing but this. We can express this in the format of this. We can take this function a cos omega 0 t plus phi into this format. We can write this in this format. This is a real part and this is the imaginary part. You can see that from the equation. We just in this section it is just been described in this. That's a cos omega 0 t plus phi is equal to a real e to the power j omega 0 t plus phi. In case of imaginary, the imaginary value is this and real value is this. We can describe this function as this. As can we can describe this function as this. It means that complex exponential signal is nothing but a sinusoidal signal. That is the transformation of this, because both are this function basically express or refer to the same signal, or referring to the same signal. Okay, let's go to the next slide. This is the example of a different, with a different frequency, the sinusoidal signal is behaving or expressing in a different way. In case of first signal, look, the frequency is high. In case of the second signal, the frequency is much lower than this signal, and in case of this, the frequency is again much lower from the second signal. But in the case of third signal, the frequency is much lower than the second signal. Let's go to the next slide. Now, the same thing can be expressed with discrete time complex exponential signal, and this can also be converted into a sinusoidal signal. What you have written here, that as in continuous time, an important signal in discrete time is the complex exponential signal or sequence, basically a sequence defined by x function of n. In case of this is same, c alpha to the power n, where c and alpha are in general complex numbers. This could be alternatively be expressed in the form x function of n is equal to c e to the power beta n, where alpha is equal to e to the power beta. The same thing, we just convert this, we just replace this alpha with e to the power beta, nothing else. And this is the example. There are pictorial depiction of different kind of discrete time complex exponential signals. Okay, these are the different kind of complex exponential signals. Now again going to describe the same thing that we have described in case of continuous time complex exponential signal, where we convert, we basically express that discrete time complex exponential signal and continuous time complex exponential signal, both can be described or referred as a sinusoidal signal, as a function and as a signal. Okay, here we have done the same thing. We taken the e to the power j omega 0 n. We can also describe it as this, as we can describe this as a this, and we can also describe a cos omega 0 n plus phi as a real part, as an imaginary part. In case of discrete time signal, in place of t, we take n, which is an integer value. In case of t, the value of t will be continuous, it will not discrete. But in case of n, we are taking a very important fact is that we take an integer value, discrete value 1, 2, 3, 4. But in case of t, we are taking a continuous value. We don't pause or start it. That's the difference. Let's go to the next slide. And now there's a very important fact that I have to describe. Take a very closer look here. The periodicity properties of discrete time complex exponentials, signals. Absolutely, we're talking about signals only. In order for the signal to be periodic with n is equal to 0, we have this. If you take a very closer look here, the same thing will happen if e to the power j omega 0 or anything. We can take anything basically. So omega 0 basically refer to fundamental frequency. Omega is equal to 2 pi f. F is the frequency, and f0 is the fundamental frequency, and omega 0 is basically referring to 2 pi f0. All the fundamental things will be expressed as t suffix 0 or f suffix 0 or omega suffix 0. Okay. Now e to the power j omega 0 plus n plus n. N is the integer value of the signals, and plus n is the number, is the integer value which after every which this signal will be repeated as a periodic signal. Now the same thing will there, e to the power j omega 0 can be, you can return this as a this. Okay, sorry. Okay. Okay, so when you have yes, and e to the power j omega 0 big N is equal to 1. Now in case of 1, we can put e to the power j 2 pi. So omega 0 will be omega 0, and we can, from this value we can take this omega 0 n is equal to 2 pi n. Why? Because in case of 1, where we have e to the power j 2 pi n. Now m is nothing but, that is, there must be an integer m such that for the signal we get this. N is the value after each of n is the value, suppose 3. After 3 integer value, the same signal will be repeated. That's why n has been considered. And n is a multiple value of 2 pi. It means after 2 pi, every 2 pi, suppose 2 pi into 4. After every 4 into 2 pi, after this 2 pi repeated, the signal will be repeated also. That's the point of 2 pi m. M is nothing but we can take m is equal to 1 also. That's the point. Okay, let's go to this next slide. Okay, these are the signals that I have described. Here there are different kind of signals are there. Okay, different kind of signals are there. Look, this is cos 0. Each and every function has described the basic periodicity of the signal. Now, in case of this, what you have to describe is a very important factor that I need to consider here, that we have to, in this case, what you have described is very important factor is that there is a basic difference between continuous time signal and discrete time complex exponential. In case of continuous time complex exponential signal, continuous time complex exponential signal, what we have the value of t. With the value of t, the signal will be varied. Now, if we get back to the previous slides, what we have here, yes, there. This is a continuous time complex exponential signal. Or we can express it as a sinusoidal signals. In case of sinusoidal signals, what we have is e to the power j omega 0 t. In case of t, with the variation of t, the signal will be act according to it. It is just repeating itself after a specific time interval. It's come back and go. This is the basic. Now, in case of discrete time complex exponential signal, there is a basic difference between both of them. And what is that is, in case of complex exponential signal, the value of n will not change. This value will not change. It will just come back again and again, similar to that. And so omega 0, as the omega 0, if we take consideration of the omega 0 is going to change each and every time. It means that simply, if we take a even value, if we take a even multiple of 2 pi, or pi, what will have, that frequency of the signal is less. The frequency of the discrete time complex exponential signal will be lesser. But if we consider the odd multiple of pi, the frequency of the discrete time complex exponential signal, or sinusoidal signal, will be high. It means in case of even multiple of pi, the signal frequency will be low, and for odd multiple of pi, the signal frequency will be high. That's the basic difference. In case of continuous time complex exponential signal, this thing will not be considered. Now, this is what you look. If this is the signal is differing. Here the frequency is low. In case of this, the frequency is high. That's the basic difference. It means it closer to the even multiple of pi. In case of this signal is closer to the odd multiple of pi. That's the basic difference. That's why this different signal will be constructed. This different signal, same function, but the signal frequency will be different. Both of these are same function. The signal will be described the same function, but the frequency will be different according to the position of the integer value. Where it is, in case of odd multiple, the frequency will be high of the signal. This signal will be closer. This bar will get closer, and in case of even multiple, of pi, the signal will be much more wider than each other. The frequency will be different. Even multiple for frequency, and that's what I've described in earlier. This is the same thing. This is the equation that we need to consider. Okay. Thank you for that. We'll get to the next lecture later.